All right, so chemists. Yes. Yes. The question is about the test. We haven't even started the lecture. We already. So the test will be on chapters 17 through 19. So it'll be all acids and bases all the time. So 20 and 21, we still have not decided what will happen with that. So, because that will be on term, either way, it will be on term 4. Okay. Yeah, so we'll figure it all out. All right. So, chapter 20, solubility equilibria. When you see equilibria and equilibrium, what do you immediately think? K. And when you think of K, what else do you think of? Concentrations and something else we all love. Rice charts. So this is another chapter of a decent number of rice charts, although they tend to be a little bit easier with solubility equilibria. So up until this point, really in your academic careers, we had categorized salts as either soluble, which means they totally dissolve in water, or insoluble, which means they don't dissolve in water at all. The truth is a little bit more gray than that. So we assume that they dissolve and dissociate completely if they are soluble, whereas in reality, the solubility depends on what the salt is, whether or not you have other ions in solution, and what the pH of the solution is. So the first thing we're going to do is take a look at the actual steps involved in dissolving. So if we have solid NaCl, what do you think that, how should I represent solid NaCl? Yeah, Ben. Alternating Na and Cl. So I'm just going to go plus, plus, oh, plus, 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 plus. Now I think there was a question on the AP exam last year about the size, relative size of these ions. I have not drawn them to scale. But if I did, which one would be larger? Which ion would be larger, Na or Cl? Talk about it at your tables for a second. Back to the cards. All right, so blank, blank for sure. Carter, which one's bigger? Yeah, the Cl ion is bigger because that gains an electron, stays in the third energy level, and actually gets a little bit larger because of the extra repulsion. Na plus loses an energy level when it loses an electron, so it's significantly smaller in size. All right, so water looks like this. Now, once we dissolve it into water, I want to show you guys, again, I've showed you this before, but just so we're all on the same page. If I take table salt and I put it into water, it says, shake me. Yeah, that table salt does look gross, but so what happens to the sodium chloride? Yeah, in this case, it completely dissociates. I don't have any NaCl formula units still bonded together. Okay. So we can see now they're just sort of randomly moving until they collide with each other. So do this. And we go back here. Okay. So, whoops. So now we have and how do the water molecules align themselves around these ions? Yeah, Johanna. Yep. So you're just matching charges. So the H is partially positive, so it's attracted to the negative ions. The O is partially negative. So what you end up getting is, I'm going to go up here. So if I have my Na, which is plus, I actually get a number of water molecules that surround the ion. And this is called a hydration shell. Those waters aren't locked into place, but they generally stay in that arrangement where the partially negative oxygen sticks close to the Na+. And if it were the Cl-, the partially positive hydrogens would be there. Okay. So let's look at dissolving and enthalpy. So as we are at towards the end of the year, hopefully a lot of the things were, God, I feel strange like having to like consciously keep myself like slow. Yeah. It's like it's very strange to keep myself like slow. Okay. So we're trying to put lots of things together. God, I'm like boring myself. We put lots of things together at the end of the year. So dissolving and enthalpy. So there are 3 steps energetically that go into the dissolution process. The first thing we're doing, we have to separate the ions. And when we separate ions, we're breaking bonds. So one of our most fundamental principles, if we are breaking bonds, what does that mean about our delta H? Who's confident? If we're breaking bonds, what does that mean about our delta H? Oh, come on. Yeah, Ian. Sorry, I want new voices. What is it, Ian? Greater than 0. Yeah. So this is endothermic. Energetically, this is a pretty big delta H. Bigger than the next one, which the water molecules have to separate to accommodate the ions. It's not that the ions go into like blank space. The water molecules have to move. So here, you're disrupting intermolecular forces. So we're separating things that want to be together. So what does that mean about our delta H? our delta H, with confidence, Joanna, is positive. That's right. So this is endothermic as well. So if these were the only steps, would we consider this to be thermodynamically favorable? No, because it's both of them take energy. But the last step, where you have the hydration shell forms around ions. Now here you have attracted things that want to come together. So your delta H is less than 0. So this step is exothermic. And we're going to call this delta H1, delta H2, and delta H3. Yeah, Alexi. Yeah, so the question was, I drew the hydration shell with just O surrounding the positive. And does it happen with the H's and the negative? Yes, it does. So like the Cl would have a hydration shell with negative, with because Cl is negative, the H's would be surrounding the Cl minus. No such thing. So the question, that's a good question. What's to stop the solution from just creating a lattice structure like this? I'd say, I'm not 100% sure is the answer, but I would guess that your concentration of solute is generally small compared to your concentration of solvent. So these are actually, each individual ions aren't super close to each other all the time. And the ions also move. And it's not, when they move, they don't take the same water molecules with them necessarily. It might be other water molecules that supplant. So this, the hydration shell, the waters around it are fluid. So they're not locked into place like this. It's just a representation. It's a good question. Okay. So our overall delta H, Griffin, give me a color. Quiet veranda. I'm giving that a green because it's got the ver. So your delta H of solution is equal to your delta H1 plus delta H2 plus delta H3. So this is going to be positive, this is going to be positive, and this is going to be negative. And the sign of delta H depends on the relative strengths of attraction. So we have the ion-ion attraction. We have the water-water attraction. And then we have the H2O and ion attractions. So our delta H depends on the strength. On your thermodynamics test, I think there was, at least on the practice test, if not on the real one, there was a question about something dissolving in water, but the water solution got colder. So in that case, our delta H of solution was positive. If the water heated up, our delta H of solution would be negative. So this is one part of thermodynamics, is delta H. What's our other part? Delta S. So how about dissolving in entropy? Here we want to look at really at two major steps. The ions go from solid 2 aqueous. What would you think the sign of delta S would be? Talk at your tables just for a second, and I'm going to go to the cards. All right, Cameron, what do you think? Yeah, delta S is going to be greater than 0. The ions are free to disperse throughout the liquid. Whereas when they're solid, they're locked in place. But also, we have water forms a hydration shell. So water is sort of arranging itself around the ions. So as water arranges itself around the ions, is that more order or less? More. So delta S is less than 0. It's more ordered. The question was, should we number the delta S's? No, you don't have to. So in most cases, overall delta S is greater than 0 because step 1 has a larger magnitude. However, number 2 can sometimes win. So most of the time, the entropy that you gain is going to be greater than the entropy you lose. Okay. So now we're going to talk about soluble versus insoluble salts. These are not things that you need to memorize. These are just general rules of thumb. So when we say a salt is soluble, like sodium chloride, that means we can dissolve about 0.1 mole or more in 1 liter of water. Insoluble is 0.001 moles, and slightly soluble is somewhere in between. We're going to be calculating a lot of these things, but in general, which salts, what are the most important rules for solubility that we remember? First group, so Li, Na, K, Rb, Cs, are always going to be soluble. There's another 2 ions that generally make soluble salts. NH4 plus is one of them. The other one's an anion. So, yes, Nora, it is 3 minus. It's okay. It's all right. Yeah, NO3 minus. So these are going to be group 1, NH4 plus, NO3 minus, generally. Just to remind us of our solubility rules. Okay. So here's the first thing you should know from this chapter. When an ionic compound dissolves, the equilibrium constant expression contains nothing in the denominator because the reactant is a solid. So, for example, consider the dissolving of the salt calcium fluoride. So we have this equation So what is the K value for this, Ben? There you go. And now we're going to have a new K. So we've had K, we've had Ka, Kb, Kw. Now KSP, where SP is called the solubility product. So now we have KSP to add to our ever-growing list of Ks. The F minus should in fact be squared. Yes. Thank you, Alex. So now what does it mean to have a saturated solution? It means that equilibrium exists between solid, compound, and ions in solution. Now, if I have a salt that is in equilibrium and I add more solid, so say I have equilibrium of calcium fluoride with Ca2 plus and 2F minus, and I add more calcium fluoride, what's going to happen to my equilibrium? So talk about it at your tables for a few seconds. If I add more calcium fluoride to a system in equilibrium, what's going to happen? Okay, so Trevor, what do you think is going to happen if I added more CF2? So it would favor the reactants? Favor the products? So we've had favoring the reactants, favoring the products. Favoring the products. All right. Who agrees that it's going to favor the products? Oh, wow. Even your own group is leaving you out on an island. Wow, that's not nice. That's not nice. Okay. So, Ian, what do you think is going to happen? Favor the reactants. Okay. All right. So, who agrees with Ian that it's going to favor the reactants? You're adding solid CF2. Okay. Azika, what do you think? Reactants? Okay. All right, so your group, what did you guys say? So nothing's going to happen? All right. What do you guys think? What? Nothing happens? All right. Yes, the correct answer is nothing happens. Well, I think we need to work on group work here and supporting our peers, because I didn't see a lot of support. All right. Okay. So guys. So Nora, why is it not going to shift anything at all? Yeah, solid CAF2 is not in the K equation. So when you add more solid CF2, it does nothing to a system that is already at equilibrium. So additional solid does not yield more ions. So up into that point, you can keep adding solid and ions will form. But once you hit equilibrium, it doesn't matter how much solid you add. you're at equilibrium and you can't get more. So I want to show us what this looks like once everybody's done copying. Okay, go back here. Now, if I keep adding salt, even something that's soluble like salt, all right, that would be not pleasant to drink. I don't know. The question was like, can you add the perfect amount so that they all match up? Right. To get to a saturated solution, one of the best ways to do it is to oversaturate and then filter out the solid. So the question is what, Edward? So the question is, why does the dissolved and bound numbers keep changing? Because remember, at equilibrium, we're generally, not changing, but it changes like a small amount here. You'll notice what I wanted to show you here is that ions will go back into the solid and then aqueous. So you can actually see the reaction is happening in both directions, but in general, we're at equilibrium where the numbers don't change much. Yeah, Carter. So the question is, if I evaporated all the water, would the salt recrystallize? And I don't think I can evaporate. Another one has the ability to evaporate. But this does not. So yes, it would recrystallize. Mm-hmm. So the question was about salt we get out of our salt shaker. I'm not 100% sure what the practice is for manufacturing salt on a large scale. What's that? There might be salt mines. You could also get it from seawater. Like you'll see sea salt. But sea salt's got other stuff in it too. We also iodize our salt. So we put iodine in it because iodine deficiencies can lead to problems with your thyroid. So that was a big problem in the old days, but now we all get sufficient iodine from our iodized salt. So I'm not sure what the process is. So now if I have a slightly soluble salt, let's pick one. Silver bromide. So now you can see it takes a lot less for me to be at equilibrium. I have a lot less solid silver bromide than I did sodium chloride, but I'm already at equilibrium. So this is slightly soluble. I could design a salt. Yo. Okay, sorry, could you say that again? I have a fully saturated solution. And I put a chunk of salt in it. Could it change shape? Yes. Yep, so it probably would change shape. I don't know what the time scale would be for you to see anything. But yeah, if you left it for a couple days, I would imagine eventually it will just settle on the bottom. Yeah. Right, so the question was, is like the statement was if you had a whirlpool, it would just form like that. So in industrial processes, you're always mixing, right? So you would have that in industry. Okay. All right. Now let's go back here. The second thing you should know. We can calculate the extent to which a compound dissolves based on its equilibrium constant, or its, or its KSP. Okay. Now, these are easier Rice charts in general. If we look at this example, the KSP of silver chloride is 1.6 times 10 to the minus 10th. What is the molar solubility of silver chloride in pure water? Well, let's start with, so Caitlin, what's my chemical equation for the dissolution of silver chloride? All right. So this is the first step in our Rice chart. So Daniel, what can I disregard immediately? Yeah, so this whole side gets crossed out. And so Griffin, give me another color. Palm breeze. I was thinking of blue. Is it turquoise? All right. This is the best light blue I can get. All right. So if initially I have 0 here, what is my change going to be? Plus x plus x. So equilibrium, I have x and x. So my KSP is Ag plus times Cl minus. So I know 1.6 times 10 to the minus 10th equals x times x, which is x squared. So I solve for x, and I get 1.26 times 10 to the minus 5th moles per liter. Yes, Carter. So the comment was, and it's a true comment, in this case, you don't even really need the Rice chart, because you know it's like x squared equals the KSP, and you solve for x. It's going to get a little trickier, but you should probably still be able to see. When you will probably need the Rice chart is when we start adding in concentrations of ions that are already there. But for now, you can probably just see it and do it. Okay, speaking of one that's a little bit more complicated, at your tables, I want you guys to do this one. Figure out what is the molar solubility of bismuth sulfide. Be careful. What's your KSP expression? All right, I have seen nobody get it all the way right yet. Everybody's making the same mistake. Oh, yeah, you're on the track. All right. So where I see most people is right here. So stick with me just a minute. Most people are good up to here, and they see, okay, plus 2x, plus 3x. And so at equilibrium, they have 2x and 3x. Now, the two things that I've seen people do most commonly is they set x to the fifth equal to KSP. That's not right. I've also seen people do 6x to the fifth equal to KSP, which is also incorrect. Here's what you have to do. KSP equals 2x squared times 3x cubed. You have to plug your equilibrium numbers into the equilibrium expression. So you get 1.1 times 10 to the minus 73 equals 27 x to the fifth. Sorry, 108. I forgot. See how easy it is to make mistakes? 108. All right, so tell me when you think you have an x. Do we have agreement? Good, because that's what I have too. Okay. So that's why this, Carter, back to your question, this one, it's a little better to use the Rice chart because you can see it and know what to plug in a little bit more easily. Okay. Example 3. Now we have 50 milliliters of 0.01 molar lead nitrate mixed with 50 milliliters of 0.01 molar silver chloride. Will a precipitate form? So on your blue sheet, you have KSP values. So start by writing out the chemical equation for this reaction. So write out the chemical equation for the reaction between lead nitrate and sodium chloride. All right, at this point, I think you should be here. Now, we know that that is a solution and that is a solid. So really what we want for this is the net ionic equation. So we have Pb2 plus AQ plus 2Cl minus AQ makes PbCl2 solid. So really what we're looking for now is we're making this a Q versus K. Because if the ion concentration is too low, no precipitate will form. Okay, so what's the KSP value for lead chloride? On your formula sheet. Yeah, go ahead. 1.6 times what? 10 to the negative 5. I have a different one. I have something times 10 to the minus 7th, but I could be wrong. PbCl2, what is it? 1.6 times 10 to the negative 5th? Okay, cool. All right. So now we have to see really what we want to look at. This is the way that the reaction for the K reaction is generally written. It's a solid going to the ions. Well, my K for this is equal to Pb2 plus times Cl minus squared, which is equal to, you guys said, what was it, 1.6 times 10 to the minus 5th? Now my Q for this is also the same. Remember, Q is just the snapshot of where you are, and you compare it to K to figure out if you're there or not. So what's my concentration of Pb2 plus? There's a little trick here. Yeah, go ahead. Right. So the trick was you had to cut it in half because you're diluting it, right? And your Cl minus is also that, but it's squared. So really we get 5 times 10 to the minus 3 cubed. Which I don't know what that is off the top of my head, but I know you guys have calculators that you can solve these wonderful mathematical. That doesn't help me either. 1.2 times 10 to the minus 7th. I see where, okay. Now, compare, this is my Q. My Q is still less than K. That means my ion concentration is too small, which means no solid will form. So really what happens is the salt continues to dissolve and dissolve and dissolve until the point where you reach your KSP value. And at that point, the solid will stop dissolving. So in the case of this chemical reaction, we mix the two together, and we would not see a precipitate form. That's the type of question you might get. This is mixed with this. Do you see a precipitate form? And it has to do with the KSP value. So if your Q is less than K, you're not going to see a solid form. Okay. We will end here today.